quick synopsis of the ideas we covered on Friday, October 4th. First, differentials. Given some function y equals f of x, if we find the derivative as a function of x, we can denote that as y prime, the derivative, or f prime of x, or the derivative with respect to x of function y, which we can simplify to dy over dx. So dy and dx, these are differentials. So what are differentials? Let's take a look at what they are visually. Consider some graph of y equals f of x. Consider a tangent line at some point x. We know that the tangent line has a slope that is the instantaneous slope of our green function, which we could denote f prime at x. If we move delta x to the right, then this value will be x plus delta x, and that stands for the actual change in the x value. So at that x value, the change in the y value in our green curve is from here to here. That's the actual change in the y value. From this green dot to this green dot, this green segment is the actual change in the y value. So if this distance is delta x wide, the actual change in the x value from this point to this point, and if this dimension is the actual change in the y value, then if we use our linearization, our linear model that's representing the green curve, especially near values of x. For a linear model, if we go to the right, that's going to be our differential in x, and it says only go up this high, and that's our differential in y. So the change in y according to our linear prediction is the differential y, whereas the actual change in y is delta y. Okay, if y is equal to f of x, and we take the derivative of both sides, then we'll have dy dx equals the derivative with respect to x of f, which we could say is f prime of x. And if we treat the differential ratio as actual ratio of real numbers, we can multiply both sides by dx, and that will give us a formula for the differential of y. And the formula for the differential of y is f prime of x dx. However, now let's look at the same formula derived from the geometry of what differentials really mean. Focus on this yellow right triangle and the slope of its hypotenuse. Well, the slope of the hypotenuse is the slope of this gray tangent line, which is f prime of x. But in terms of Algebra 1 material, the slope of a segment is the rise over the run. So from this green dot to the red dot, the slope of that segment is the rise, dy, over the run, dx. So let's come over here and explain this algebraically. The slope of the gray tangent line is f prime of x, but it's also the slope, it's also equal to the value of the slope of the hypotenuse, which is rise over run, dy over dx. And so if we solve for dy right here, dy is equal to f prime of x times dx, which is exactly what we had before. But this derivation shows geometrically why the differential y is equal to f prime of x dx. And that concludes this little discussion, this 4-minute discussion about what differentials are and how dy is different than delta y.